Let's do an example of a problem where the question doesn't clearly say whether the object is stationary or moving, and go through this whole process. So in this problem here, we have a block sliding down a ramp, as I showed you before, but this time we don't know, you could have a ramp where I release it and the object actually stays at that location on the ramp, or if you increase the ramp angle, say, now it slides down. So what's going to happen in this case? It's a 10-degree box on a 30-degree ramp. The coefficients of friction are given. Is it going to slide down the ramp? And if so, what will be its acceleration? Or is it going to have acceleration equal to 0 because it's just going to be stationary? Okay. Step 1, draw the free body diagram. So a lot of this is going to be similar to the other ramp problem I solved. So I'll go through it a little bit quickly, but we'll have gravitational force will go straight down. We'll have normal force perpendicular to the ramp, and we'll have friction force parallel to the ramp, holding it back that way. And get rid of this little thing here. Okay, let me label my forces. This is mg. This is friction, and this is normal. And this is a 30-degree angle here, the angle of the ramp. And as we showed in previous video, that means this is a 30-degree angle here. So now I've got my diagram. As I previously said, what I'm going to call my coordinate system here is that this direction will be the positive parallel direction, and this direction here is going to be the positive perpendicular direction. So I'm using a rotated coordinate system. Okay. So I need to break all my forces into components next. So I have normal force, I have friction force, I have mg force, are my three forces. Okay, normal force is in the positive perpendicular direction. It has 0 parallel component. Friction force is in the positive parallel direction. It has no perpendicular component. And by the way, I'm not even worrying at all about whether it's static or kinetic friction yet. The thought has not even crossed my mind. What I'm doing right now for the friction force only depends on its direction. It has nothing to do with the magnitude of the friction force. So this part is totally irrespective of whether it's static or kinetic friction. Okay, now the mg force, this is in the negative parallel direction and the negative perpendicular direction, and it's going to be mg sine of 30 over here and mg cosine of 30 over here, because I am picturing, remember, a triangle like this. Oops. Let's see if I can draw this a little bit neater. I'm picturing a triangle like this with the right angle over here. So the perpendicular side is adjacent to the 30-degree angle, and the parallel side is opposite of the 30-degree angle. Okay, and lastly, I should also think about the direction of my acceleration vector. I don't know if there is an acceleration yet, but if there is, it's going to be down the ramp in that direction, which is the negative parallel direction. So let me throw that in here as well, and 0 in this direction. Okay, so there's my setup. Now I can actually start writing down equations. Again, I'm still not worried about whether it's static or kinetic friction just yet. I'm going to wait as long as possible to make that assumption. So in the parallel direction, actually, let's do the perpendicular direction first, because the perpendicular direction doesn't have any friction in it. So this part is not going to depend on whether it is static or kinetic friction. We're going to get normal force minus mg cosine 30 equals 0. which gives me normal force equals mg cosine 30, which I can actually plug in. It's 10 times 9.8 times cosine 30 equals 84.9 Newton. Okay, so there's my perpendicular equation. Now my parallel equation. I'm going to have friction minus mg sine of 30. Let's plug that in too. M is 10 times 9.8 times sine of 30 equals 49 Newton minus, no, that's it. And then this will equal minus M is 10 times A. So my equation looks something like that. Okay, now, at this point, I need to make an assumption about whether friction is static or kinetic. If I assume friction is static, I can plug in A equals to 0, but I don't plug anything in for the friction force. If I assume kinetic, the A stays in there, but I can plug in for the friction force. So I want to assume static. Let me change pen colors to emphasize the fact that I'm now making an assumption. So I'm going to assume static friction, because that's what you have to assume first, remember, if you don't know. So when I assume static friction, the friction force, I can leave that alone, but the acceleration now goes to 0 because everything is totally stationary. That means my friction force is 49 Newton. Okay. Now I also need to know F max. Let me switch pen colors again because F max actually doesn't depend on my assumption. F max, I'll write over here, is mu sub s times normal force. So that's 0.4 times 84.9. And that is about 34. Okay. So the next thing I do is I compare the maximum possible friction force is 34. My proposed value of the friction force is 49. So I compare these to each other and I say, okay, if the system is static, the friction force has to be larger than F max. Does that make any sense? No, because something can't be larger than its maximum value. That's impossible. So this makes no sense, which means static friction is wrong. So I have to throw away everything I wrote in blue there. I don't have to throw away anything I wrote in red, because everything I wrote in red, I waited as long as possible to assume that it was static friction. So everything I wrote in red is still fine. Let me switch pen colors again. And now assume kinetic friction. It's not really that much of an assumption anymore because I've just proven that it's not static. And if it's not static, it has to be kinetic. But nevertheless, let me switch pen color. So for the kinetic friction case, now I can plug in FF is mu sub k times Fn. So we're going to plug in, well, let's do it one step at a time. So mu sub k times Fn minus 49. Let me drop the units because I don't have a lot of space here. And this will be minus 10a. And now mu sub k is known. That's 0.2. Fn is known from over here. That's 84.9. And then minus 49 equals minus 10a. So 0.2 times 84.9 is 16.98. So basically, let's call it 17. So 17 minus 49 is minus 32 equals minus 10a. As expected, I got a positive acceleration because I've already included the negative sign. So a represents the magnitude of the acceleration vector. So it's about 3.2 meters per square second pointed down the ramp, and I'm done. So what the question was actually asking is, what's the normal force? That's here. It's the same one calculated in red. And second question, what's the box's acceleration? That's here. So question answered.